Hello friends, welcome to my lecture on initial and final value theorems for Z transforms. In practical applications, often we need the values of un for n equal to 0 and n tends to infinity without actually requiring the complete knowledge of the sequence un. We know that the sequence un is related to the its Z transform uz. So, by using that relationship we can find the values of un for n equal to 0 and n tends to infinity without actually knowing the sequence un. So, suppose the Z transform of un sequence is known, it is given by uz, then it turns out that the value of un for n equal to 0 is given by limit of uz as z tends to infinity. The proof is quite simple. We can see the definition of the Z transform. uz is given by which is Z transform of the sequence un is given by sigma n equal to 0 to infinity un z to the power minus n, which when expressed as u naught plus u1 z plus u2 y z square and so on taking the limit as z tends to infinity gives us the value of u naught as limit z tends to infinity uz. So, when we take the limit of this equality as z tends to infinity, we get limit z tends to infinity uz as u naught. So, this limit of uz as z tends to infinity gives us the value of u naught. Now, similarly we can see that limit z tends to infinity z times uz minus u naught is equal to u1. So, in order to see this we have uz equal to z of u1 sequence, which is sigma n equal to 0 to infinity u1 z to the power minus n, which is u naught plus u1 y z plus u2 y z square and so on. So, from here we see that uz minus u naught multiplied by z, this is equal to u1 plus u2 by z plus u3 by z square and so on. And so, taking the limit as z tends to infinity, z times uz minus u naught gives us the value of u1. Similarly, from equation 1 we can see that uz minus u naught minus u1 by z, uz minus u naught minus u1 by z, when it is multiplied by z square gives us u2 plus u3 by z plus u4 by z square and so on. Okay. So, taking the limit again as z tends to infinity, okay, we get limit z tends to infinity z square times uz minus u naught minus u1 by z equal to u2 and so on. So, this is how we can get the initial values of the sequence un by its Z transform. So, let us now talk about the final value theorem. Here we will get the value of un as n tends to infinity. So, if the Z transform of the sequence un is known, say it is uz, then this result tells us that the final value of the sequence un, that is un as n tends to infinity, is given by the limit of z minus 1 uz as z tends to 1. Let us look at the proof of this final value theorem. So, we can take the z suppose we take the z transform of the sequence un plus 1 minus un, then by linearity property we can write it as z of un plus 1 minus z of un, and then we use the shifting property here, shifting to the right, shifting of the sequence un to left. So, z of un plus k is z to the power k into uz minus u naught minus u1 by z minus u2 by z square and so on minus uk minus 1 z to the power k minus 1. If we use this shifting property, then z of un plus 1 will be equal to z times uz minus u naught. So, we will get z of un plus 1 equal to z times uz minus u naught. So, let us substitute the value of z of un plus 1 here. So, z of un plus 1 minus un is z times uz minus u naught minus uz, and then we can write this further as uz times z minus 1 minus u naught z. Now, by definition of z transform of the sequence un plus 1 minus un is equal to sigma n equal to 0 to infinity un plus 1 minus un into z to the power minus n. As z tends to 1, then we will have limit z tends to 1 z minus 1 uz minus u naught as limit z tends to 1 n equal to 0 to infinity un plus 1 minus un z to the power minus n, because z minus 1 into uz minus u naught z is equal to this. So, from this equation and this equation we arrive here as z tends to 1, limit of this expression is equal to limit z tends to 1 this. So, when z tends to 1 it will tend to sigma n equal to 0 to infinity un plus 1 minus un, which can be expressed as limit n tends to infinity this its partial sum, another partial sum. So, u1 minus u naught minus u2 minus u1 n plus un plus 1 minus un, and this will reduce further to un plus 1, limit n tends to infinity un plus 1 minus u naught, which is equal to limit of un as n goes to infinity minus u naught, because u naught is independent of n. So, then we can cancel and the left hand side is limit z tends to 1 z minus 1 uz minus u naught, because u naught is independent of z. So, we can cancel u naught on both sides, and then we get limit of un as limit z tends to 1 z minus 1 uz. So, this is the proof of the final value theorem. Let us use this initial value theorem to find the initial values of the sequence un when its z transform is known. So, let us say uz is known to us and we want to determine the value of un for n equal to 2 and n equal to 3. So, let us see how we get this. Uz is equal to 2z square plus 5z plus 14 divided by z minus 1 to the power 4, okay. And the initial value by initial value theorem u naught, the initial value of the sequence un, u naught is limit z tends to infinity uz. So, this is equal to now uz can be written as in the numerator we have a polynomial of degree 2 in z and the denominator has the polynomial in z of degree 4. So, I can write it as 1 by z square 2 plus 5 by z plus 14 by z square divided by 1 minus 1 by z to the power 4, on taking z square common from the numerator and z to the power 4 common from the denominator. So, this will get, we will get this. Now, as z tends to infinity, this expression tends to 2, this tends to 1. So, this whole thing tends to 2 and this goes to 0. So, the limit is 0. So, we get the value of u naught as 0. Let us now find the value of u1. u1 is equal to limit z tends to infinity z times uz minus u naught. So, this is limit z tends to infinity z times 2z square plus 5z plus 14 by z minus 1 to the power 4 minus 0. So, uz can be expressed in this form. When we multiply this form by z, okay, what we get is 1 by z. So, this z cancels with one z here and we get 1 by z, 2 plus 5 by z plus 14 by z square divided by 1 minus 1 by z to the power 4. Again this expression tends to 2 and this goes to 0. So, we get the limit as 0. Now, let us find u2. Okay. So, u2 is limit z tends to infinity z square times uz minus u naught minus u1 by z. u naught and u1 both are zeros, and when we multiply uz by z square, okay, what we get is limit z tends to infinity 2 plus 5 by z plus 14 by z square, 5 by z divided by 1 minus 1 by z to the power 4, and when z goes to infinity this limit clearly is 2. So, we get the value of u2 as 2. We can similarly find u3. So, similarly u3 is equal to limit z tends to infinity z cube times uz minus u naught minus u1 by z minus u2 by z square. Now, we have obtained u naught as 0, u1 as 0, u2 equal to 2 by z, u2 equal to 2. So, we can find the limit. So, u3 is equal to limit z tends to infinity z cube times uz is 1 by z square, 2 plus 5 by z, 5 by z plus 14 by z square divided by 1 minus 1 by z to the power 4 minus this is 0, this is 0, this is 2 by z square. So, 2 by z square. Z cube can be multiplied. So, this is limit z goes to infinity, z cube when multiplied gives you 2z plus 5 plus 14 by z divided by 1 minus 1 by z to the power 4 minus 2, and we can simplify it further to find the limit. So, this will give you this z cube when multiplied, this is 2z. So, 2z times this. Okay, now we can write it further as one minus 1 by z to the power 4 can be expanded by binomial expansion. So, we have 1, then 4 times minus 1 by z, then 6 times minus 1 by z square, then we have 4 times minus 1 by z cube, and then we have 1 by z to the minus 1 by z to the power 4. So, we can do this. Now, we can see when you multiply 2z here, and what then happens? So, 2z minus 2z, 2z cancel out, we have then 5 okay. So, we 2z cancel out, we get 5 plus 14 by z, okay, and here what we get, this z cancel out, we get minus 4 into minus 2. So, plus 8, and then this z when multiplied here to z square, what we get is minus 12 into 1 by z, and then we get here minus 1 by z cube. So, we get plus 8 times 1 by z square, and then we get minus 2 times 1 over z to the power 3. So, when z goes to infinity, this goes to 0, this goes to 0, this goes to 0, and what we get is 13. So, this is equal to 13. So, this is how we get the value of u3. Now, this is example 1. In example 2, we have taken an example of inverse z transform. Let us find inverse z transform of ln z over z plus 1. So, we shall apply the power series method to determine the inverse z transform. Let us see, ln z over z plus 1 is equal to ln z plus 1 over z to the power minus 1, and this is ln, or I can say this is minus ln 1 plus 1 by z. Now, if mod of z is greater than 1, then I can write it as minus 1 over z minus 1 over 2 times z is 1 by z square plus 1 by 3 times 1 by z cube, and so on, provided mod of z is greater than 1. So, I can write it as minus 1 by z plus 1 by 2 z square minus 1 by 3 z cube plus 1 by 4 z to the power 4, and so on. Now, comparing this series, infinite series, with sigma, we note that here there is no term which is free from z. So, we get z inverse. Okay. So, if so z inverse of ln z over z plus 1, this is equal to un sequence. Okay. Then un is equal to 0 when n is equal to 0, and so here when n is equal to 1, the coefficient is minus 1, when n is equal to 2, the coefficient is 1 by 2. So, we get minus 1 to the power n divided by n when n is equal to 1, 2, 3, and so on. This is the example 2. Let us now go to the next slide and see how we find the inverse z transform of z over z plus 1 whole square. We know that z transform of n into a to the power n is az over z minus a whole square, provided mod of z is greater than mod of a. So, when mod of z is greater than mod of a, we know that z transform of n a to the power n is equal to az over z minus a whole square. So, taking a equal to minus 1, we have z transform of n times minus 1 to the power n equal to minus z divided by z plus 1 whole square, provided mod of z is greater than mod of minus 1. So, which is 1, and this gives us inverse z transform of. So, using the linearity property of the z transform, what we get is minus z transform of n times minus 1 to the power n minus 1 is equal to z over z plus 1 whole square when mod of z is greater than 1, or we can say that inverse z transform of z over z plus 1 whole square, this is equal to minus 1 to the power n minus 1 into n. Now, this is the method where we have used the known result to get the inverse Z transform. There is a method which we call as long division method. We can find the inverse transform by using that long division method also. So, let us see how that method works. So, we shall apply the long division method. What we will do here is that we have z over z plus 1 whole square. Z over z plus 1 whole square is z over z square plus 2z plus 1. So, let us divide z by z square plus 2z plus 1. We have to divide z by z square plus 2z plus 1 in such a way that it will lead us to an infinite series in powers of 1 over z. So, z square plus z plus 1 by we multiply this by z to the power minus 1. So, that here when we multiply by z to the power minus 1 we get z here. So, that z will cancel with this z here. So, z to the power minus 1 we take, then we multiply z to the power minus 1 here. So, we get z plus 2 times z into z minus 1 is 2 plus z to the power minus 1, and what we get is when we subtract the sign changes. So, minus 2 minus z to the power minus 1. Now, our aim will be to eliminate minus 2. So, we write here minus 2 times z to the power minus 2. So, when you multiply minus 2 times z to the power minus 2 to z square, you get minus 2, and then we get minus 4 z to the power minus 1, and then minus 2 times z to the power minus 2. Again we subtract. So, we sign changes and this cancels, and we get 4 z to the power minus 1 minus z to the power minus 1. So, we get 3 z to the power minus 1 plus 2 times z to the power minus 2. Now, we multiply by 3 times z to the power minus 3. So, that when we multiply it to z square, it will give us 3 times z to the power minus 1. So, 3 times z to the power minus 1, and then we get 6 times z to the power minus 2, and we will get 3 times z to the power minus 3. So, like this we continue. So, we will get here 4 times z to the power minus 2 with a negative sign, minus 3 times z to the power minus 3. So, now our aim will be to multiply z square by an expression which will give us minus 4 z to the power minus 2. So, minus 4 z to the power minus 4. So, minus 4 z to the power minus 2, and then we get minus 8 z to the power minus 3, and then we get minus 4 z to the power minus 4. So, this is plus this cancels, and we get this minus, this is 5 times z to the power minus 3 plus 4 times z to the power minus 4. So, continuing this process. Okay. So, thus z over z plus 1 whole square, it will come out to be z to the power minus 1, then minus 2 times z to the power minus 2, and then 3 times z to the power minus 3, minus 4 times z to the power minus 4, and then next one will be plus 5 times z to the power minus 5, and so on. Okay. And when we compare it with that series sigma un z to the power minus n, so this gives us then z inverse of z over z plus 1 whole square. This is equal to this is equal to u(n) equal to 0, because there is no term contain which is free from z. So, 0 when n is equal to 0, n minus 1 to the power n minus 1, when minus 1 to the power n into n, when n is equal to 1, we will write here minus 1. So, this is how we get the inverse z transform of z over z plus 1 whole square. With that I would like to conclude my lecture. Thank you very much for your attention.